just to give you a little overview of what's coming next, and the lesson we're about to do, this is going to be working with just like multiple neurons in a single layer. Then after that, we'll talk about building out multiple layers. Okay, so this is multiple neurons in a single layer, then multiple layers. And then there's just like a couple of special layers in a neural network, mainly the final layer, the output layer, and also the layer, really the data. Here we'll talk about what the input layer of a neural network. And then finally, we'll go back towards PyTorch and seeing how we can use our knowledge to now not just build a neural network with a single neuron, but with multiple neurons. Let me close Slack. All right, so let's get to it. All right, so we'll start with how we always start, which is with the hypothesis function of a single neuron, right? And remember, what is that? Well, this is that dot product of w dot x plus b, and this should output me a value between negative infinity and positive infinity, so any potential value. And then we know we take the output from this linear layer and we pass it through the sigmoid function, and that gives us a range of values between 0 and 1, where the closer we are to 0, the more confident we are that, in a negative prediction, closer we are to 1, more confident we are in a positive prediction. Just to review this dot product thing, because this is what we'll be going now deeper in this lesson, remember that W is a vector, right? This is our weight vector, and X is a vector as well. That's our feature vector, okay? So when we say, what we can imagine this being in our breast cancer example, well, maybe this is, right, the cell area and the cell concavity, right? How large is the cell, how many bumps, right? And then we remember that we're going to weigh these features differently. And for the dot product, as we know, we pair together the entries of our vectors by the index. So first goes with first, second goes with second, pair them together, multiply the pairs, and then add the products. Okay, so that's the dot product. And then finally, we add our bias term. All right, so remember, this was our linear function, and we kind of use the dot product as a way to summarize that linear function as w dot x plus b. All right. Okay. So just to review, right, here's our features. We say cell area is 2, cell concavity is 1. This is a single observation. We imagine that like we've already maybe trained our neural network and we've come to these values of 3 and 4, right? And then we finally have this bias term, and then to pass this data through our linear layer, we get this w dot x plus b. We hope that it works. Okay, cool. And it got to 2. So let's just double check the math. 2 times by 3, 1 times by 4, that's 6, plus 4 is 10, minus 8 should give us 2. So that works fine, but remember what we want to do is not just use a single neuron, but a whole layer of neurons. That's what we're focusing on here. So like, what does it mean to really use a layer of neurons? And even like, why would we want to use a layer of neurons? So back to this breast cancer example, let's think about this. Let's say we have even more features this time. So for example, maybe we have the cell area in the perimeter. So 2 things that kind of deal with like the size of the neuron. Okay. And then we also have the number of concave points. And when we say symmetry errors, right, like how much does the left side look like the right side? So this is dealing more with like the shape. But in all, there's 4 total features, right? 4 attributes now about each cancer cell or potentially cancerous cell that we're gathering. Okay, so now instead of 2 attributes or 2 features, we're using 4. All right, and now we say that maybe we want a neuron, but even though we have kind of these 2 categories of features that describe the size and features that describe the shape, maybe we'll have a neuron that just specializes or really zooms in on the neuron size. So what does that look like mathematically? This is a neuron. It's going to take in all the attributes of this cell, of this potentially cancerous cell, but it's going to zoom in on or focus on the size attributes. Okay? So what that means is, mathematically, is that these weights that correspond to the size are going to be larger, or have a larger absolute value than the weights that correspond to the shape. Okay? So you can kind of see this. This neuron is weighing size more than it's weighing shape, right? Those are the features that are going to influence it more. An increase in the area by 1 will increase the output of this linear layer by 2. An increase in perimeter by 1 will increase the output by 3, right? Whereas here, it's only going to nudge it by 0.5, reduce it by 0.5, and here it has no impact at all. So you can kind of see that we now have a neuron that specializes in just one, in just the size, assessing the size of, I should say, the cell. Okay. So, just to drive this point home, we do have weights that correspond to all of the features, but they're larger, they have a larger absolute value when it comes to the size. And that's effectively a neuron that's specializing or focusing in on just the size of a cell. And then we have a second neuron. So this second neuron, this guy's going to be focused on the shape. All right. So notice this is again our feature vector. So this represents our cell, and I'm using exactly the same numbers just to say, hey, this is the same observation, has the same features and same feature values. But this time, when you look at the neuron, we have a neuron that now focuses in on the shape. So what does that mean? It means that the weights corresponding to size are closer to 0. They have a smaller absolute value. And the weights corresponding to shape, those are larger. They have a larger absolute value. So the take-home point from this, right, we have one neuron that focuses on size, one neuron that focuses on shape, is that when you think about a layer, well, there's almost like a specialization that each of these are like workers, and each of them have like a specialized skill set. This guy's really focusing on size and taking in that potentially cancerous cell and assessing the size. This guy's feeling around for the shape, right? Maybe this guy's looking at the color. Okay, this guy's looking at light and darkness in general. So now we kind of have like this team of neurons, and they focus in on different features, right, of that same observation. All right. And the way that works in practice is we simply have larger numbers or weights with larger absolute values that correspond to those specific features. So this guy's focusing in on size, this guy's focusing in on shape, okay, and is more sensitive to changes in shape because of these weights. So, to get the prediction, I guess the other thing you can see is that each of these neurons is making a prediction or making an assessment about that observation, that potentially cancerous cell. This guy, its assessment is all about the size, right? 1.5. This guy's assessment is all about the shape, whatever that means. Maybe -3 means very lopsided or something, or very weirdly shaped. So this guy is, is making a separate assessment. So we're getting kind of like two different outputs, one from each neuron, but they're focusing on they're saying different things to us. So the takeaways, kind of like a summary, is that we have different weights for each neuron, right? We have two neurons that we worked with, one that handles size, one that assesses shape. And we have different weights, right? These are larger when it comes to the size features. These weights are larger that correspond to the shape features. But the other point is that they're fed they're fed the same observation, and therefore these values are the same. Okay? So I'm feeding the same, potentially cancerous cell to two different workers and having them each kind of tell me, okay, yeah, I took a look at this cell. Here's the assessment about the size, and this guy goes, okay, take a look at the cell. Here's the assessment about the shape. But they're looking at exactly the same observation. So that's what this looks like. And we should also get familiar maybe now with this diagram. So this is the x1 through x4 that we saw before, right? These are the 4 features, okay, of that one observation. Let's even copy this. All right, so we had 4 features here. And so this is like the 4 features of an observation. And the point is that these 4 features, all of these 4 features, 1, 2, 3, and 4, are all going to this neuron assessing size. And all of these features, hold on, can I do this? 1, 2, 3, 4, are all going to this neuron that's assessing shape. And all the features, now I guess for this diagram, I added in 2 more neurons. But the point is that all of the features are going to every single neuron in the layer, right? Even though it focuses in on, these attributes for size, and this neuron focuses in on these attributes for shape, all of the data is getting passed to each of the neurons. That's what these both are illustrating, right? All of the features are getting passed to this neuron, all the features are getting passed to this neuron, and it's up to the neuron to decide how it's weighing the features, right? Cool. Okay, so that's what this diagram looks like, and now hopefully we can understand it. So this is just saying we have an observation that's 4 features, and in this diagram, I guess it's being assessed by 4 different neurons, okay? And each of these neurons is just applying the dot product, but they are using a different weight vector for each of these neurons, and a different bias, I should say. Now, so this is, how we summarize, what we saw before with one observation, or single observation, has these different features, 2, 4, 3, 1. And then this guy's assessing the size, this guy's assessing the shape. By the way, you can see I'm kind of removing the bias for now. We'll add it back in. I just want to focus in on this dot product that we were applying. So this is assessing the size, this is assessing the shape. Now, in linear algebra, we can actually shorten this. Instead of doing 2 separate dot products, we can write these are equivalent, okay? So here we did the dot product, and we got 2 times by 1, 4 times by 3, 3 times by this times by this, and we got 12.5, right? We multiplied the pairs, and then we added those products. And then here we got 8.5. Here we're multiplying this, and we're taking the weights and putting them in one column, and we're putting these weights in a separate column, okay? And now we're applying the dot product again, or you could call this even vector matrix multiplication if you want. And the way vector matrix multiplication works is you just simply take this vector, and you dot it with the first column, and you get the output, right? Same exact dot product, same exact output as the first entry. Then you take the vector, same vector, you dot it with the second column, and you get that output that we saw before. So this is really just, previously we did 2 separate operations, and linear algebra says, okay, we can, make this more brief by putting these vectors into a matrix, and then applying the dot product twice. Okay, apply it on this, apply it on that, and this column, this dotted with this, produces the first output. This dotted with the second column produces the second output. And more generally, right, if we have a vector x and we have a weight matrix that has one neuron's weights in the first column, which is always how I think is generally how we'll have it. One neuron's weights in the first column, another neuron's weights in the second column. Then our operation is x.w1 is going to be our first entry, x.w2 is going to be our second entry, and then we get these 2 outputs, right? These are our weighted sums, right? Because we didn't add in the bias term yet. And then just to keep going, so illustrating the same point, now let's see it in code. So maybe you'll believe me. That we have this W size. These are our values. They're actually, I guess this was, really more 0, negative 0.5. This is really what we called our W shape, all right? And then this was our W size. It doesn't really matter. And then we'll put in W size and W shape. So that's exactly what we saw here. 1, 3, negative 5, 0. 1, 3, negative 5, 0. And now if I do, and here I have 0, negative 0.5, that's exactly what I have here. So now if I do W dot X, I should get those same values, and I do not. Oh, I don't think I can do dot anymore. I think I have to do at. Nope, size mismatch. 4, 2. So we just need to do, sorry, this is X dot W. We'll talk about that later on. Oh no. Yeah, this will work. Okay, X at W. Sorry for the errors. But you can see, hopefully, that worked, right? We're taking this and we're applying the dot product or matrix multiplication to each of the vectors. And if we were to just do this one by one and just say, okay, X times by dotted with the size, we get 8.5 the first entry, and X dotted with the shape, we get 11 the second entry. So that's the point, right? This is vector matrix multiplication. Just, think of this as two separate vectors. Each column is a separate vector, and you take our weight vector, dot it with our feature vector, dot it with our first weight vector, take our feature vector again, dot it with our second weight vector. Cool. And I just say, okay, what is a matrix? A matrix is a rectangular array of numbers arranged in rows and columns. This is a matrix, right? We kind of think of it as these two vectors side by side. So like I said, here we just did we focused on the weights. There's no mention of the bias here. So if we add in now the bias, so previously we did this just with the weights. Now we add in the bias. Well, you can do X dotted with our weight matrix plus a bias vector, where we have a separate bias for each one of our neurons. In doing that, we simply add, negative 12 to that first output and add negative 7, I suppose, to that second output. Okay. So now if we had, let's just look at this. If previously we had this, so dotting it produced us, 8.5 for the first neuron, 11 for the second one. And now I do plus B. Then I get negative 12 plus 8.5 and negative 7 plus 11. And that should give us negative 12 plus 8.5 should give us negative 3.5. Negative 7 plus this output 11 should give us negative 4. Is that right? I did something. Oh, I came close. I just messed up that. Oh, this was 11, I think. Let's just see that again. Yeah, this was 11, so 11 minus 7 is 4. All right. Cool. So you can see that, okay, to add the bias, we get a separate output from each entry. And with the bias, we just say, okay, we have this bias vector where we have a separate bias term for each of our neurons, and we just take this first neuron's bias, add it to this value from the dot product, take our second neuron's bias, add it to this second output. Okay, so in other words, it's kind of like entry-wise addition, right? 12 plus 8.5, negative 7 plus 11. You get the point, I think. Okay, so this is it. This is our linear layer using multiple neurons. This is, maybe you can even this, maybe at the beginning of this lesson felt complicated, but now maybe you can understand this. X dotted with this whole matrix. What does that mean? It means that we take this vector, which represents a single observation, and we have these two neurons, one that assesses maybe the size, and the other that's more focusing in on the shape, and we dot all the features in this observation with all the weights, right, of this first neuron. and we get this. Then we dot all the those same features of the potentially cancerous cell or the observation with the second neuron, and we get this. So this gives us two different numbers, right? Before we saw it was 12, now we saw it was 8.5 and 11. So this gives us 8.5 and 11, and then we add in those bias terms, one from the first neuron, the other one is from the second neuron, to finally get two outputs from our linear layer. And this whole thing we can summarize as this, right? X dot W plus B is X dot W plus B, where Z is a vector consisting of the output of each neuron's linear function. Well said. Okay, so here I guess I give you guys a quiz, and I'm like, if we have this neuron, these weights from these two different neurons, right? Here's the weights of one, here's the weights of the other, and then we have X. Let's move this down. The question is, what is X dot W, or X multiplied by W? Right, so we can find the answer like this, but let's see if we can calculate it. Well, really what we want to do is do the dot product of this guy. I'll just write it 2, 0, 1, 2, dotted with this vector X. So it's like this. I'll just say dot. All right, so what is that? That is 4, right? 2 times 2 is 4, plus 0. That's nice. Plus 3. Plus 2. And then let's go to the second one. 1, 1, 2, 0. So the same values of X, this time dotted with 1, 1, 2, 0. And what does that equal? Well, that is 2, 4, right? 2, 4, 6. Oh, that's nice. 2, 4, 6. Then 0. And what does that equal? That equals 12, I think. All right, 6 plus 6 is 12. 4 plus 3 plus 2 is 9. And it breaks because it just doesn't like, see this, whenever you see this expected scalar type long but found float, we just have to worry about like coercing the data, I believe. So we'll change it all to float because it's the most flexible. Actually, I'll do it down here. I'll say X dot float added with W dot float, and there we go. And we got different answers. Maybe W new. That's the problem. W new. 9 and 12. Perfect. Look, I can do it. Okay, so this is just the linear layer of multiple neurons. So we're dealing with multiple neurons, but we're just dealing with the linear layer at this point. But no more. We're going to move on to the activation layer because it's actually not that hard. That's why we're combining this in one lesson. Because what we do is you just apply that sigmoid function to each of the entries, each of the outputs in that linear layer. So what does that mean? Well, if this is what we were getting, it breaks again because of this X, we'll call everything a float, dot float, dot float. And now we get our outputs. Okay, now if we got the outputs, right, from two different neurons, so these are our outputs from our linear layers, and now this gets passed, each one of these outputs gets passed to our activation layer. So this is a negative number, so it becomes close to 0. This is a large positive number, so it becomes close to 1. So we can think of this as like this neuron's lighting up telling us, hey, this guy is maybe like really small, this cancer cell, this observation, and this guy, or so it's, I guess it's not lighting up, it's pretty dark. And this guy is lighting up saying, hey, it's pretty misshapen, perhaps, right? So they're making two different assessments based on these weights, and we get those responses, these outputs of Z, and then we use that sigmoid function to apply the sigmoid function to each of these entries, right? So again, it just looks like this, X dot W plus B. Notice I'm using a capital letter W. This is by convention. We try to tell us what kind of data we're working with in math. So this is indicating when we see a capital W, that means we're working with a matrix. When you see lowercase, the assumption is could be a vector. Sometimes it could even be not a vector, a single number. But here they're both vectors, right? So what we had, if we have X, a feature vector, dotted with a weight matrix, plus our bias vector, right? Feature vector, weight matrix, dotted with a bias vector. That's going to give us a separate output, like 12.5, and let's say I think it was and let's say -5 for each of our neurons, right? This gives us one output for here, one output for there. Then we add the bias term. We get two separate outputs here. And then from there, we apply the sigmoid to each of those two entries. So it was 12.5, -5, right? You apply it to each of these. And that gives us back a number, two numbers between 0 and 1. So maybe this one's really high, and this one's pretty low, 0.03. And these now have these neurons that are making these two different assessments. One that's assessing, hey, this is, I guess in this case, a really large cell. And this one's making an assessment that this is, maybe not such a misshapen cell. Okay? So that's pretty cool. So you can see that what's happening here, let me just scroll up to this picture, is that each of these guys, right, are making these different assessments. And what we'll want to do is take the values, take the assessments from this layer and pass that data to the next layer, right? Until finally, this able to take this information and make a prediction as to, all right, this is cancerous, this is not. This is the number 5, this is the number 3, right? So we'll have to see how to do that. But you can see that what's happening at this layer is we're just making kind of these individual assessments about the same observation. And hopefully you saw that we did that simply by applying the dot product, really, once for each of these neurons. Cool. All right, next up, we'll see how to pass data from one layer to the next layer.